20.4 Adiabatic processes for an ideal gas. In this session, we will explore several key topics related to the thermodynamics of ideal gases. We begin with the quantization of molecular energies and how temperature affects the population of excited states. From there, we will define adiabatic processes and derive the mathematical relationships between pressure, volume, and temperature when no heat is exchanged. Finally, we will apply these concepts to a practical example involving the compression cycle of a diesel engine. Quantum physics shows us that the rotational and vibrational energies of molecules are not continuous, but are instead restricted to specific, discrete levels called quantized states. On this slide, an energy level diagram illustrates these states for a diatomic molecule. The vertical axis represents increasing energy. The longest horizontal lines represent vibrational states, which are separated by large energy gaps. Within each vibrational level, you can see shorter, more closely spaced lines representing rotational states. For these motions to contribute to the molar-specific heat of a gas, the molecules must gain enough energy to undergo a transition from their lowest energy ground state to an excited state. The internal energy of a molecule is directly proportional to its temperature. At low temperatures, such as 50 Kelvin for hydrogen gas, the thermal energy is too low to excite the molecules, so they remain in their ground states. In this regime, only translational motion contributes to the internal energy. As the temperature rises to intermediate levels around 500 Kelvin, the molecules gain enough energy through collisions to reach excited rotational levels, which then contribute to the specific heat. At very high temperatures, near 5000 Kelvin, the energy is sufficient to excite the vibrational levels as well. This shows that specific heat is not a constant, but changes as different degrees of freedom are activated by temperature. An adiabatic process is defined as one in which there is no energy transfer by heat between a system and its surroundings. This means the value for heat, Q, is zero. In practice, this occurs in two main ways. First, a process that happens very rapidly, such as the quick compression or expansion of a gas, is nearly adiabatic because there is no time for heat to flow. Second, a process can be adiabatic if it occurs slowly within a container that is perfectly thermally insulated. Unlike some other thermodynamic processes where one variable remains constant, in an adiabatic process, the pressure, volume, and temperature all change simultaneously. When gas undergoes an adiabatic expansion, it does work on its surroundings. Since no heat enters the system to compensate for this work, the internal energy of the gas must decrease, causing the temperature to drop. We can see this on the pressure-volume diagram shown here. The red path represents the adiabatic expansion from an initial state to a final state. Notice that the curve for an adiabatic process is steeper than the blue lines, which represent isotherms where temperature stays constant. This is because the ratio of specific heats, denoted by the symbol gamma, is always greater than 1. The governing relationship for this path is that pressure times volume raised to the power of gamma remains constant. To derive the equations for adiabatic processes, we start with the first law of thermodynamics, where heat is set to 0. This tells us that the change in internal energy, which is the number of moles times the molar specific heat at constant volume times the change in temperature, is equal to the negative of pressure times the change in volume. By combining this with the differential form of the ideal gas law and using the relationship that the gas constant equals the difference between the molar specific heats at constant pressure and constant volume, we arrive at a differential equation. Integrating this results in two key state equations. First, pressure times volume raised to the power of gamma is a constant, and second, temperature times volume raised to the power of gamma minus 1 is also a constant. Let us look at an example involving a diesel engine cylinder. Suppose air at 20 degrees Celsius is compressed adiabatically from an initial volume of 800 cubic centimeters and a pressure of 1 atmosphere down to a final volume of 60 cubic centimeters. Using a gamma value of 1.4, we first find the final pressure. By multiplying the initial pressure by the ratio of the initial volume to the final volume raised to the power of gamma, we calculate a final pressure of 37.6 atmospheres. To find the final temperature, we use the ratio of the final pressure and volume to the initial values. The temperature rises significantly from 293 Kelvin to 826 Kelvin, which is 553 degrees Celsius. In summary, we have learned that molecular rotational and vibrational states are quantized and only become active at specific temperature thresholds. An adiabatic process is characterized by the absence of heat transfer, meaning Q equals 0. For an ideal gas undergoing such a process, the product of pressure and volume raised to the power of gamma is constant, as is the product of temperature and volume raised to the power of gamma minus 1. Finally, it is important to remember that adiabatic expansion leads to the cooling of the gas, while adiabatic compression results in a significant increase in temperature. To wrap up, consider these review questions to test your understanding. First, think about why the molar-specific heat of a diatomic gas increases when the temperature is raised from 50 Kelvin to 500 Kelvin. Think back to the activation of different molecular motions. Second, looking at a pressure-volume diagram, why is the curve for an adiabatic process inherently steeper than the curve for an isothermal process? Reflect on the mathematical role of the ratio of specific heats and how the change in internal energy influences the pressure drop during expansion.